Hi everyone, in this video we will learn about curl and divergence, which are two basic operations that can be performed on vector fields. One of them will give us another vector field and the other will give us a scalar field. And you will be, especially if you are in engineering, you will be seeing a lot of these in your classes at some point. So the first, let's jump into the first one. The first operator is called curl, and we're going to look at its formal definition and see that it's actually connected to another mathematical operation that you've done before. So the assumption, we start with a vector field f given component wise is pi cap plus qj cap plus rk cap. It's a vector field on R3, which means it's three space, a regular three-dimensional space. And we assume that the partial derivatives, all of the partials, so with respect to x, y, and z, for each of the vector functions p, q, and r exist. Then the curl of f is defined as this expression, which in its current form, as it's written, looks slightly complicated. There's a certain symmetry in here. So you have partial of r with respect to y, subtract partial of q with respect to z. Then you have a partial of p with respect to z, subtract partial r with respect to x, and a partial q with respect to x, and a partial p with respect to y. However, this entire thing can be written in a much neater form. To do that, we have to recall this operator, del. This del operator, which we saw when we learned about how to find the gradient of a vector field, is essentially the three partials, del x, del y, del z, written in a vector notation with a I cap, j cap, and k cap. And we also remember that according to this notation, if you take a vector field f and you take the del of it, it's basically saying you take partial with respect to x in the I direction, so convert it into a vector, partial of f with respect to y in the j direction, and partial of f with respect to z in the z direction or k cap direction. So that's what this looks like. Now, since these are vectors, right? So if you look at del, this is a vector. And del operated with a vector field gives us another vector of this form. So what basically happens is the curl of f is cross product of this del operator with the vector f. How? Let's see. If we are to find the cross product of this particular vector, finding cross product, we use a determinant. We use a 3 by 3 determinant. We always write ijk, and then we write the components of each vector. What are the components of this vector? The components of this vector are the individual partial operators, del x, del y, and del z. And the component of f vector is p, q, and r as per our assumption. And now, when you write out this determinant, for I cap, right? So let's use this. So for I cap, it's going to be this cross and then a subtract, right? So if I write that down, that's going to be del r over del y minus del q over del z I cap, which if you go up there, that's exactly what it was in the not very nice sort of notation over there, or expanded notation. Similarly, when you're working with j cap, it's going to be cross of these vectors. So for j cap, I'm going to have del p over del y minus del q over del x j cap. And then lastly, for k cap, I'm going to have, I made a mistake. The j cap one is wrong. I'm going to delete all of these and this. So j cap would be this and this, which would make it minus, or replacing the plus, will be del p over del z minus del r over del x j cap. And lastly, the k cap is going to be a cross over here. So that would be del q over del x minus del p over del y, k cap. So this operation on vector field curl is, the easiest way to remember this is that it's the cross product between the del operator and the vector field f itself, which can then be found using the determinant. Let's look at an example. Suppose a vector field is given to you in this form, and you have to find the curl of this vector field. The solution is pretty straightforward. Essentially, it just comes down to first writing this curl as a cross product between the del operator and your vector field, then writing out the determinant. So this is always going to be del x, del y, del z, because the operator del doesn't change. And these are the individual components. You have xz, you have xyz, and you have negative y squared. Once you're done with that, you will have to compute a bunch of these partials, right? So first, let's see, what do we have for I cap? So for I cap, we have del over del y of negative y squared minus del over del z of xyz. So that's in the I cap direction. Minus, in the j cap direction, we have del over del x of negative y squared and del over del z of xz j cap, and lastly we have partial with respect to x of xyz and partial with respect to y xz k cap. Working this out, partial of this is negative 2y, partial with respect to z is xy. Sorry, that's a subtract here, so this should be 2y or negative 2y minus xy I cap. Partial of negative y squared with respect to x is 0, and this will be x j cap, and yz, and partial with respect to y is 0, so yz k cap. So putting this all together, factoring out a y, 2 plus y, negative y I cap plus x j cap plus y c k cap, which itself is a vector field, which makes sense because if you go all the way back to Calc 3, you will recall that when you learned about operations on vectors, there were two kinds of multiplications. There was the dot product and a cross product. Dot products give scalars and cross product give vectors. So these are vectors because the curl is a cross product. Okay, so that's kind of straightforward. Now we have a theorem which we will prove here, and this is also pretty straightforward. In proving, it says if f is a function of three variables and it has continuous second order partial derivatives, then the curl of the gradient of f is 0. Okay, so another way to say this is it's basically saying that the curl of a gradient vector field is 0. And the proof of this is pretty straightforward. We just have to write out the definitions. So what does the curl of this mean? Now first of all, we got to verify that this is a vector, which it is because a gradient is a vector field. But what is curl? Curl, we just saw, is cross of del f, which we can write out once more as a determinant because it is a cross product, with the second entry always being the del operator. Now in this case, the vector field is the gradient of the scalar field f. So this is del f over del x, and del f over del y, and del f over del z. And if you expand this out, we will get, for I cap, for example, the second partial, so del squared f over del y del z minus del squared f over del y del z, which is what? They cancel each other out, that is 0. So you would expect the same thing happening everywhere else. You get a del squared f, del z del x, and a del squared f, del x del z, j cap, and a del squared f, del x del y, minus del squared f, del y del x, k cap. All of this is just 0. And why is that? Well, remember the theorem which says that these orders, if you change them for second order partials, they are the same. So we have a nice result that if you take the curl of a gradient vector field, it is always 0. Now, recall something from the previous topics, which is we had something called conservative vector field, which I mentioned is that it's going to reappear, and it's very important, especially in physics and engineering. A conservative vector field is one that has, or that can be written as a gradient vector field. So it's f is conservative if we can write this as the gradient of some scalar field small f. Also recall other consequences of conservative field about path independence and all of those things for line integrals. So putting this together, we just saw that the gradient, right, field has a curl of 0. So this tells us that if f is conservative, we now have another way to check if something is not conservative. Then the curl of f has to be 0. So this means that, what does this imply? As a tool, what this gives us is to check if a vector field is conservative, you just find the curl. Find the curl and see if it is non-zero. Because what does this result say? This says that if f is conservative, then curl is 0. Which means what is also true is that if the curl is not 0, then f is not conservative. So it gives us a nice way to check this. This is the same vector field that we just looked at, and so the solution to this is pretty straightforward. We already have the curl of this vector field, which we found to be negative y 2 plus x I cap plus x j cap plus yz k cap, which is not 0. And when we say 0, we mean identically 0, which means it's 0 always, right? Not because of certain sentences being true and all of that. Then this gives us another theorem, and this time it tells us when something is conservative. It says that if f is a vector field defined on all of R3 whose component functions have continuous partial derivatives and curl is 0, then f is a conservative vector field. So there are some necessary conditions here, which include that all the component functions of that vector field have to have continuous partial derivatives, and if the curl is 0, then f is a conservative field. Show that this function is this vector field is conservative. Now, previously, in order to do that, we would have to find some scalar field small f, whose gradient would give you capital F, which we saw was a slightly more difficult task. Or we'd have to do something with line integrals and all of that. However, now we have a very a standard procedure for doing something like this, which is to simply take the curl. So repeating this determinant structure, ijk del x del y del z, x squared z cubed, 2xy z cubed, 3xy squared z squared. So let's see what's happening in the I cap. I'm going to perform the partials here. So we have partial with respect to y, which is 6xy z squared, minus partial with respect to z, which is 6xy z squared. So that's for I. Then I have j cap. For j cap, it's going to be partial with respect to x, which is 3y squared z squared, and partial with respect to z, which is 3y squared z squared. And then lastly, for k cap, we have partial with respect to x, which is 2yz cubed, subtract partial with respect to y, which is 2yz cubed, and all of this just comes out to 0, which implies that f is a conservative vector field. So that's one of the types of problems that you will have, which is finding or checking if a given vector field is conservative or not. So last thing is, why does this name curl come from? Well, curl, it gets the name curl because it is related to rotation. It's because it measures rotation or rotational tendencies in vector fields. One of the simpler ways to think of this is in terms of motions of fluid, whether certain fluids are have rotational movements around them or not. When something doesn't have rotation or that the curl is 0, then it's also called being irrotational, which is a physics term. So, for example, if you look at these two fields, there's some clear distinction between what's going on here. If you look at the field on the left, there are some sort of a circularity going on here, some sort of a circular motion. There are little eddies being formed over here. So here, the curl of this vector field would not be 0. It would be some non-zero quantity, non-zero vector, because there are circular movements here. Whereas the curl over here would be 0, because if you look at any box here, things are either leaving or entering, and there is no definite rotational circular motion that is happening. That brings us to an end for this part of this section, which is curl. The next idea that will be covered is going to be divergence, which is the second basic operation on vector fields. So that's it for this video.